Good morning, ma'am. My name is M. Ashwita. I am from Computer Science and Engineering Department. Now, I am here to give a presentation on minimum cost spanning tree in advanced data structures and algorithm analysis. Let's go to the next slide. Outline of my presentation. Introduction to minimum cost spanning tree. Key concepts. Properties of minimum cost spanning tree. Algorithm for finding minimum cost spanning tree. Prim's algorithm and example. Pascal's algorithm and example. Application of minimum cost spanning tree. Complexity analysis. Limitations of minimum cost spanning tree. Comparing algorithms and conclusion. Let's start our presentation. Introduction to minimum cost spanning tree. A minimum cost spanning tree is a subset of edges from a connected graph. It connects all vertices in the graph without any cycles while minimizing the total edge weight. Understanding minimum cost spanning tree is essential in network design, optimization problems, and resource allocation. Suppose you have a connected undirected graph with a weight or cost associated with each edge. The cost of a spanning tree would be the sum of costs of its edges. A minimum cost spanning tree is a spanning tree that has the lowest cost. This is an example for minimum cost spanning tree. Key concepts. A spanning tree includes all vertices and uses the minimum number of edges necessary to connect them. The total weight of a spanning tree is the sum of weights of its edges. Minimum cost spanning tree aims to minimize this total weight compared to all possible spanning trees. Minimum cost spanning tree. Every minimum cost spanning tree will contain the minimum weight edge that connects two components. Any edge not in the minimum cost spanning tree that increases the total weight cannot belong to the tree. All spanning trees for a graph have the same number of edges, specifically v minus 1 edges for v vertices. This is an example. This is a graph. So this net graph has 10 edges. The spanning tree has only n minus 1 equals to 7 edges. Here, here the number of vertices is 7 and number of edges is total 10. So we have a formula is v minus 1 edges. So n minus 1 equals to 7 edges. Algorithm for finding minimum cost spanning tree. The two most commonly used algorithms for finding minimum cost spanning tree are one is Prim's algorithm and another is Kruskal's algorithm. Both algorithms efficiently construct a spanning tree while ensuring the minimum total edge weight. Understanding the differences in their approaches is crucial for selecting the appropriate algorithm. Let's see one by one. Prim's algorithm. Prim's algorithm starts with a single vertex and grows the spanning tree one edge at a time. It always chooses the edge with the smallest weight that connects a vertex in the tree to a vertex outside the tree. This greedy approach ensures that the tree remains connected and minimizes the total edge weight. In Prim's algorithm, we can see that uh, one vertex is connected with another vertex only in a cyclic manner. But cyclic manner. Let's take an example to find the minimum cost spanning tree using Prim's algorithm. The left side is a weighted tree, so we need to find the minimum cost. So in the name only suggests that minimum cost spanning tree. The first we should take an edge with minimum cost. In this tree, the minimum cost is 10. So from vertex 1 to vertex 6. So first we represent that is A. From 1 to 6, the 10. The in the tree, the next minimum cost is 14. But Prim's algorithm clear. But in Prim's algorithm, the in the structure will be formed as a tree. So then the next will take from 6 to 5 or 1 to 2. Then from 6 to 5 is less when compared to 1 to 2. So then we draw a edge between 6 to 5. Next, from 5 to 7, we have an edge from 5 to 7 and 5 to 4. But when compared to both 5 to 4 having less cost. So the next will represent an edge between 5 to 4. Similarly, from 4 to 7, 4 to 3, the edge is the edge cost is minimum for 4 to 3. So we represent that in that represent is in D. And from 3 to 2, the cost is 16. And similarly, 2 to 14, 2 to 7 is 14, 2 to 1 is 28, but the minimum is 2 to 7. So represent 2 to 7. When we'll take from 7 to 5 or 7 to 4, the graph becomes cyclic. So it does not satisfy the spanning tree property. So the tree should final tree should be a spanning tree means the tree should not be in cyclic form. So that final answer will be this. Next, another type of approach is Kruskal's algorithm. Kruskal's algorithm starts all edges in the graph by weight and adds them one by one to the spanning tree. It only adds edges that do not form a cycle with the already selected edges. This algorithm is efficient for sparse graphs and is based on the union find data structure. If we take in Kruskal's algorithm, uh, while we are finding the minimum cost spanning tree, it does not need to form a tree. We can take which weight is less, so we'll draw for that first. Now let's take an example to find the minimum cost spanning tree by using Kruskal's algorithm. This is a graph. So by using this graph, first we'll write the cost in ascending order from 1 to 6, 10. Again next 3 to 4, 12. 2 to 7, 14. 2 to 3, 16. 7 to 4, 18. 4 to 5, 22. 5 to 7, 24. 5 to 6, 25. 1 to 2, 28. When compared with Prim's algorithm, Kruskal's algorithm, while constructing a tree, it need not to be form a tree. So we'll construct tree with minimum cost one by one. So from 1 to 6, first is minimum. So that is represented in A. And then the next is 3 to 4. And the next is 2 to 7, that is 12. And the next is 2 to 3, 16. And the next is 7 to 4. If we draw an edge between 7 to 4, already we have an edges between 4 to 3, 3 to 2, and 2 to 7. Again, if we draw an edge between 4 to 7, it becomes a cyclic. So we eliminate that edge. Then again from 4 to 5, 22. Again 5 to 7, 24. If we draw an edge between 5 to 7 or 5 to 6 or 1 to 2, it becomes a cyclic. So we'll stop until 4 to 5, that is 22, and 5 to 6, 25. The F is the resultant minimum cost spanning tree by using Kruskal's algorithm. Applications of minimum cost spanning tree. Minimum cost spanning trees are widely used in network design such as telecommunications and computer networks. They are also used in clustering analysis and in designing transportation and distribution networks. Minimum cost spanning tree helps in optimizing resource allocation and minimizing costs in various logistical applications. Complexity animals. Prim's algorithm, when implemented with a priority queue, has a time complexity of big O E log V, where E is an edge and V is a vertex. Whereas in Kruskal's algorithm has a time complexity of big O E log E or big O E log V, depending on the sorting method used. Understanding these complexities help in selecting the most efficient algorithm for a given problem size. Limitations of minimum cost spanning tree. Minimum cost spanning trees do not account for edge directionality in different directed graphs. They may not be suitable for graphs with constraints such as capacity limits on edges. Minimum cost spanning tree does not consider vertex weights, which may be important in certain applications. Comparing algorithms. Prim's algorithm is more efficient for dense graphs, while Kruskal's is better for sparse graph. The choice of algorithm can significantly affect performance and resource usage. Evaluating the specific problem characteristics can guide the selection of the best algorithm. Conclusion of the of my presentation. The minimum cost spanning trees are a fundamental concept in graph theory and optimization. Mastering minimum cost spanning tree algorithms is crucial for solving various practical problems in engineering and computing. A solid understanding of these principles can lead to more efficient and cost effective solutions in real world scenarios. Feel free to modify any part of this outline as necessary. Thank you, ma'am. This is presented by Ashwita from Computer Science and Engineering.